What if the very fabric holding our universe together isn't cold and silent, but burning with an invisible heat? Picture this, an unseen force, making up over 1/4 of everything in existence, radiating energy we can't even feel. That's dark matter, the universe's hidden skeleton. It doesn't glow, it doesn't cast shadows, yet its gravitational grip shapes galaxies and bends light itself. But here's the twist. Scientists now believe this mysterious substance might be far hotter than anyone ever imagined. Forget what you've heard about dark matter being icy and sluggish. New evidence suggests it could be buzzing with energy, defying everything we thought we knew. How does something we can't see or touch even have a temperature? And what does this mean for the fate of the cosmos? Strap in, because the answers will change how you see the universe forever. Now let's peel back the layers of this cosmic mystery. Imagine trying to study something that refuses to play by the rules of light. That's the essence of dark matter. It's the universe's ultimate ghost, invisible yet unignorable. While ordinary matter, like stars and planets, interacts with light in ways we can see and measure, dark matter does none of that. It doesn't shine, it doesn't block light, and it certainly doesn't reflect it. But here's where things get fascinating. Its presence is betrayed by gravity. Think of it like the wind. You can't see it, but you can watch it bend trees and push sailboats across water. In the same way, dark matter's gravitational pull is so strong that it twists the very fabric of space-time around it. One of the most compelling clues comes from watching galaxies spin. When scientists first measured the rotation speeds of stars in spiral galaxies, they expected the outer stars to move slower than the inner ones, just like planets in our solar system, where Mercury zips around the Sun much faster than Neptune. But the observations told a different story. Stars at the edges of galaxies were moving just as fast as those near the center. This cosmic speed limit shouldn't be possible unless there's a massive amount of unseen matter, like an invisible hand holding those stars in place. That missing mass, dark matter, weaving an unseen web of gravity that keeps galaxies from flying apart. Then there's gravitational lensing, nature's own magnifying glass. When light from distant galaxies travels through the universe, it doesn't always move in a straight line. If there's a massive object like a galaxy cluster in its path, the light bends around it, warping and distorting the images we see from Earth. But here's the kicker. Sometimes the amount of bending is far greater than what the visible matter in that cluster should cause. That extra gravity comes from dark matter, acting like an invisible lens in space, bending light in ways that reveal its hidden presence. So, what does this mean for the cosmos? Picture dark matter as the scaffolding of the universe, holding galaxies together while also shaping the vast cosmic web that connects them. Without it, galaxies wouldn't form, or at least not in the way we know them today. Stars would scatter, structures would collapse, and the universe would look drastically different. That's why scientists often call it the cosmic glue. It's the unseen force that makes the universe as we know it possible. But here's the real mind bender. Despite making up over 1/4 of the universe's total mass and energy, dark matter is still one of the biggest unsolved puzzles in physics. We know it's there because of what it does, not what it is. And that's where the hunt for answers gets even more thrilling. Next time, we'll explore why its temperature is turning out to be one of the biggest surprises yet, and what that means for the fate of everything. Now, let's turn up the heat on this cosmic enigma. If dark matter is the universe's invisible scaffolding, what's its temperature? At first glance, that might sound like a strange question. How can something we can't even see have a temperature? But here's where things get intriguing. Temperature, in the cosmic sense, isn't just about feeling warm or cold. It's a measure of how particles move. The faster they zip around, the hotter they are. And dark matter, whatever it's made of, is no exception. Think of ordinary matter for a moment. Stars, for example, are blazing hot. their particles collide at incredible speeds, creating the light and heat we see. On the other end of the spectrum, interstellar dust is frigid with particles barely moving. Dark matter, though, doesn't fit neatly into either category. It doesn't emit light or heat, so we can't measure its temperature the way we would a star or a cloud of gas. Instead, scientists have to get creative, using clues from gravity, motion, and even the afterglow of the Big Bang itself. This brings us to the three labels cosmologists used to describe dark matter's possible temperatures: cold, warm, and hot. Cold dark matter moves sluggishly like molasses. Its particles are heavy and slow, clumping together easily to form the seeds of galaxies. For decades, this was the leading theory. It neatly explained the large-scale structure of the universe. Warm dark matter, on the other hand, moves at a moderate pace. Its particles are lighter, smearing out small-scale structures but still allowing galaxies to form. Then there's hot dark matter, which zips around at nearly the speed of light. Its particles are so light and fast that they'd struggle to clump together at all, making it a poor candidate for galaxy formation. So why did scientists initially assume dark matter was cold? The answer lies in the cosmic structures we see. Cold dark matter's sluggishness lets it collapse into dense clumps, creating the perfect conditions for galaxies to form. Observations of the universe's large-scale Webb filaments of galaxies stretching across billions of light-years seem to support this idea. But here's the twist: when astronomers looked closer, they noticed something odd. Smaller galaxies, like dwarfs, were missing. If dark matter were purely cold, there should be far more of these tiny galaxies littering the cosmos. Their absence became known as the too big to fail problem, and it threw a wrench into the cold dark matter theory. This raises a tantalizing question. What if dark matter isn't as cold as we thought? Could it be warmer, with particles moving just fast enough to smooth out those missing small-scale structures? Recent simulations suggest this might be the case. Warmer particles would resist clumping too tightly, explaining why dwarf galaxies are rarer than predicted. Even more intriguing, some theories propose that dark matter could have a mix of temperatures, like a cosmic soup with both fast and slow-moving ingredients. The implications are profound. If dark matter is warmer than expected, it could rewrite our understanding of how galaxies form, and even how the universe evolved. It would mean that dark matter isn't just a passive backdrop but an active player, shaping the cosmos in ways we're only beginning to grasp. So the next time you look up at the night sky, remember, the universe's invisible skeleton might not be as cold as we once believed. And that changes everything. Now, let's peel back another layer of this cosmic mystery by turning our attention to the oldest light in the universe, the cosmic microwave background, or CMB. Picture this faint glow as the universe's baby photo, captured just 380,000 years after the Big Bang. It's not just a relic, it's a treasure trove of clues about dark matter's hidden nature, including its temperature. The CMB is often called the universe's thermometer because its subtle temperature variations reveal how matter, both visible and dark, was distributed in the early cosmos. Imagine the universe back then as a simmering soup of particles. Ordinary matter, like protons and electrons, interacted intensely with light, creating a foggy plasma. But dark matter, unaffected by light, moved freely through this chaos, its gravity subtly tugging at the hot gas. When the universe finally cooled enough for atoms to form, light broke free, leaving behind an imprint of those gravitational tugs in the CMB's temperature patterns. Here's where it gets fascinating. The CMB is incredibly uniform, but not perfectly so. Tiny fluctuations, differences as small as 1 part in 100,000, paint a map of density variations in the early universe. These imperfections are the seeds of all cosmic structure, the galaxies, clusters, and voids we see today. But some of these fluctuations don't quite match predictions based on cold dark matter alone. For instance, certain large-scale patterns appear smoother than expected, as if something, perhaps warmer dark matter, was gently smoothing out the universe's wrinkles. Enter missions like Planck and WMAP, two space telescopes that spent years mapping the CMB with breathtaking precision. These experiments didn't just confirm the Big Bang's afterglow, they revealed anomalies that challenge our assumptions. One standout discovery, the CMB's power spectrum, a graph of how temperature varies across different scales, shows a slight but telling dip in small-scale fluctuations. This could hint that dark matter particles were moving too fast to clump tightly, effectively heating up the early universe's structure. To grasp why this matters, think of dark matter's temperature like a sculptor's tool. Cold dark matter would carve sharp, dense features into the cosmic web, while warmer particles would create softer, more diffuse structures. The CMB's smoother patches align eerily well with models where dark matter is just warm enough to resist forming overly clumpy small-scale halos, echoing the too-big-to-fail problem we see in dwarf galaxies. But the CMB doesn't just hint at dark matter's warmth, it also rules out extremes. Pure hot dark matter, like fast-moving neutrinos, would erase small-scale fluctuations entirely, leaving the universe too smooth to explain today's galaxy-filled cosmos. The Goldilocks solution, a mix or a middle ground particles with just enough warmth to explain the missing dwarfs but enough heft to build the universe's grand scaffolding. So what's next? The CMB's whispers are subtle, but future experiments like next-generation ground-based telescopes aim to listen even closer. By measuring polarization, the directional twist of CMB light, scientists hope to spot the faint gravitational fingerprints of dark matter's thermal dance. Every anomaly, every deviation from expectation brings us closer to answering the burning question: just how hot is dark matter? And with each clue, we're reminded that the universe's secrets aren't just written in the stars, but in the cold, quiet glow of its ancient light. Now, let's zoom in on the building blocks of this cosmic puzzle, the actual particles that might make up dark matter. If we're going to crack the mystery of its temperature, we need to meet the leading suspects. Scientists have spent decades theorizing about what dark matter could be, and while we haven't caught it in a lab yet, a few standout candidates have emerged, each with its own unique thermal personality. First up are WIMP, weakly interacting massive particles. These heavyweight contenders are the classic favorites, with masses hundreds or even thousands of times greater than a proton. Because of their hefty size, WIMP would move relatively slowly in the early universe, earning them the cold dark matter label. But here's the twist: even cold dark matter isn't frozen solid. Think of WIMP like boulders rolling down a hill. They're not zipping around like fireflies, but they're not motionless either. Their sluggish speed still creates a gentle warmth, smoothing out small cosmic structures just enough to explain those CMB anomalies we talked about earlier. Then there's the Axion, a feather-light particle born from theories trying to solve a totally unrelated problem in quantum physics. Axions are billions of times lighter than electrons, but don't let their size fool you. Their behavior is anything but simple. If dark matter is made of axions, quantum mechanics gives them a bizarre wave-like nature, causing them to smear out across space like a fog. This fuzzy, dark matter would act warmer than WIMP, resisting the urge to clump too tightly and potentially solving riddles like the missing dwarf galaxies. Axions might be cold in terms of mass, but their quantum jitter creates a thermal effect that's more like a low hum than absolute zero. Sterile neutrinos are another intriguing option. These are the shy, heavier cousins of the ordinary neutrinos zipping through your body right now. Unlike their detectable siblings, sterile neutrinos interact only through gravity, making them perfect dark matter candidates. But here's where temperature gets interesting. Because they're lighter than WIMP but heavier than axions, sterile neutrinos hit a sweet spot: warm dark matter. Their moderate speed would have gently blurred the early universe's small-scale structures, leaving behind a cosmic web that matches what we see better than purely cold or hot models. Now let's bust a myth. Dark matter isn't some icy, lifeless ghost. Even the coldest candidates have movement, and movement means heat, just not the kind you'd feel. Temperature here isn't about burning or freezing. It's about how particles move and shape the universe. Some models even suggest dark matter could be warmer than we thought, with particles zipping around fast enough to leave a thermal fingerprint in galaxy formation. So, why does this all matter? Because each candidate leaves a different mark on the cosmos. WIMP build dense galactic halos, Axions weave fuzzy, diffuse ones, and sterile neutrinos strike a balance. By studying these blueprints through galaxy counts, gravitational lensing, or even tabletop experiments, we're not just guessing at dark matter's identity. We're piecing together its thermal resume, one clue at a time. And with every new observation, we get closer to answering the ultimate question: what's the hidden ingredient shaping our universe? Now, let's step into the virtual universe where supercomputers are our time machines, rewinding the cosmos to test dark matter's secrets. These simulations are like cosmic video games where scientists plug in different rules, like dark matter's temperature, and hit play to see what galaxies emerge. And here's where things get weird. When they assume dark matter is purely cold, something doesn't add up. The universe should be teeming with countless dwarf galaxies orbiting larger ones like the Milky Way. But when we look up, we find far fewer than the simulations predict. It's like baking a cake and missing half the ingredients. Something's off in the recipe. This is the too big to fail problem. The name sounds dramatic, but it's spot on. The missing dwarfs aren't tiny, insignificant blips. They're massive enough that gravity should have sculpted them into visible galaxies. Yet they're ghostly absences in our telescopes. Cold dark matter's tendency to clump tightly should have left these dwarfs scattered everywhere. Their absence suggests dark matter might not be as cold as we thought. Enter warmer dark matter. Imagine stirring honey into tea. Cold dark matter is like thick honey, forming sticky clumps. Warmer dark matter is like thinner syrup, spreading more smoothly. In simulations, when scientists tweak dark matter to be slightly warmer, thanks to particles like sterile neutrinos or fuzzy Axions, those missing dwarfs start to make sense. Warmer particles move faster, smearing out small-scale clumps just enough to prevent excessive dwarf galaxies from forming. The result, a cosmic landscape that matches what we actually observe. This isn't just about fixing a glitch in the code. The too big to fail problem hints at a deeper truth. Dark matter's temperature isn't a minor detail, it's a cosmic architect shaping the universe's blueprints. Too cold and the cosmos would be littered with dwarfs. Too hot and galaxies might not form at all. The sweet spot, a warmth that smooths out the smallest structures while letting galaxies like ours take shape. And here's the kicker, this isn't just theory. Observations of real dwarf galaxies back it up. Their dark matter halos are fluffier and more spread out than cold dark matter predicts, as if something gently puffed them up. Warmer dark matter fits this like a key in a lock. It's not a perfect solve, yet science rarely is, but it's a compelling clue that we're on the right trail. So what's next? As simulations grow sharper and telescopes peer deeper, we're inching closer to pinning down dark matter's thermal fingerprint. Every mismatch between prediction and observation isn't a failure, it's a signpost guiding us toward the surprising truth. And if that truth involves a universe subtly warmed by its own hidden skeleton, well, that's a plot twist worth waiting for. Now, let's zoom in on the invisible scaffolding that cradles every galaxy, dark matter halos. These vast, shadowy structures are more than just cosmic backdrops. Their shape and density hold critical clues about dark matter's hidden temperature, acting like thermal fingerprints pressed into the fabric of the universe. Picture a halo around a galaxy not as a glowing ring, but as an enormous, invisible cloud. If dark matter were ice cold, these halos would be dense and tightly packed, like a snowball crushed in your hand. But observations tell a different story. The halos we detect are fluffier, more spread out like cotton candy spun into a loose web. This fluffiness hints that dark matter particles aren't sluggish and cold, but slightly warmer, buzzing with just enough energy to resist collapsing into ultra-dense clumps. Take the Milky Way's halo as an example. By studying how stars and gas move within it, astronomers can map its invisible mass. The data reveals a halo that's less like a compact orb and more like a diffuse, puffy cloak. This matches simulations where warmer dark matter particles, moving faster and farther, smooth out the halo's edges, preventing the extreme density peaks that cold dark matter would create. But the evidence doesn't stop there. Look at dwarf galaxies, those faint cosmic satellites. Their dark matter halos are even more telling. In a cold dark matter universe, they'd be dense knots gripping their stars in a tight gravitational fist. Yet real dwarfs like those orbiting Andromeda or the Milky Way have halos that are surprisingly fluffy. Their dark matter seems puffed up, as if gently heated from within. Warmer particles with their higher speeds naturally explain this softening, like a warm breeze dispersing fog. Here's where it gets fascinating. Some halos aren't just fluffy, they're almost cored, with a central density that plateaus instead of spiking. This is another blow to the idea of purely cold dark matter, which predicts steep, peaked centers. Instead, it's as if something smoothed out the cores and warmer particles fit the bill perfectly. Theories like fuzzy dark matter, where ultra-light actions behave like quantum waves, naturally create these cored profiles by smearing out small-scale clumps. The kicker, this isn't just about aesthetics. The warmth of dark matter halos directly impacts how galaxies form and evolve. Too cold, and halos would fragment into countless dense substructures, disrupting galaxy disks. Too hot, and halos might not form at all, leaving galaxies starved of their gravitational anchors. The observed, just right fluffiness suggests a Goldilocks scenario: dark matter warm enough to prevent excessive clumping, but cool enough to let galaxies like ours emerge. So, what's next in this thermal detective story? Astronomers are now using cutting-edge tools like the Gaia Space Telescope to measure halo shapes with unprecedented precision. Every new map of stellar motions adds another piece to the puzzle, and as we compile more evidence, the message grows clearer. Dark matter's halos aren't just passive wrappings. They're dynamic records of an invisible heat, whispering secrets about the particles that built our universe. The hunt for these thermal clues is far from over. But each observation, each halo profile, brings us closer to answering one of cosmology's biggest questions. How hot is dark matter really? And as we'll see next, there's an entire cosmic laboratory out there where colliding galaxies are putting dark matter's temperature to the test. Now, let's venture into one of the most intriguing twists in the dark matter saga: fuzzy dark matter. This theory takes everything we thought we knew about these elusive particles and flips it on its head. Instead of imagining dark matter as tiny, discrete bullets zipping through space, fuzzy dark matter proposes something far stranger. Particles so lightweight that they behave less like solid objects and more like rippling waves on a cosmic pond. At the heart of this idea are hypothetical particles called Axions. Unlike the bulky, weakly interacting massive particles, or WIMP, which were long considered the leading dark matter candidates, Axions are feather-light, billions of times less massive than an electron. Because they're so tiny, they don't just move through space, they blur into it, governed by the mind-bending rules of quantum mechanics. This means Axions don't just have position and speed, they have wavelength, spreading out like a whisper across the universe. This wave-like behavior isn't just a quirky detail, it's the key to understanding why fuzzy dark matter might be warmer than we expected. Imagine tossing a handful of sand into a still pond. Each grain would sink straight down, creating a neat little pile at the bottom. That's how cold dark matter behaves. Particles clump together densely. But with fuzzy dark matter, it's as if the sand grains dissolve into the water, creating gentle ripples that spread outward. These quantum waves don't clump tightly. Instead, they smudge out, smoothing over the small-scale structures that cold dark matter would leave behind. This smearing effect has a dramatic consequence: heat. Not the kind you feel from a fire, but a sort of quantum jitter energy woven into the fabric of the particles themselves. Because actions are spread out, their waves interfere with each other, creating patterns of high and low density. These interference patterns prevent the extreme clumping predicted by cold dark matter, leaving halos fluffier and more diffuse. In essence, the wave nature of fuzzy dark matter acts like a cosmic iron, pressing out the wrinkles in the universe's dark scaffolding. And here's where things get even more compelling. This theory isn't just elegant, it solves real-world puzzles. Take those chord halos we see in dwarf galaxies, where the density plateaus instead of spiking at the center. Cold dark matter struggles to explain this, but fuzzy dark matter nails it. The wave-like particles naturally resist piling up too densely, smoothing out the cores like butter on toast. Even better, it tackles the missing satellites problem. The fact that we observe far fewer dwarf galaxies orbiting the Milky Way than cold dark matter simulations predict. Fuzzy dark matter's smearing effect suppresses the formation of these tiny clumps, bringing theory in line with observation. But let's be clear, fuzzy dark matter isn't a silver bullet. For one, these ultra-light particles would have to be absurdly numerous to account for all the dark matter in the universe, think trillions per cubic centimeter. And their wave-like nature means they'd behave weirdly on small scales, potentially erasing structures smaller than a few hundred light-years. That's a testable prediction. If we find galaxies with ultra-fine dark matter filaments, fuzzy dark matter might be in trouble. Still, the allure is undeniable. Not only does it explain the halo shapes we see, but it also ties into deeper physics. Axions were originally proposed to solve a totally unrelated problem in particle physics: the mystery of why the strong nuclear force behaves symmetrically in time. If dark matter turns out to be fuzzy, it'd be a breathtaking example of cosmic economy, one particle solving two of science's biggest puzzles. As we push further into this quantum enigma, experiments are heating up. Labs are hunting for axions by tuning supercooled cavities like cosmic radios, hoping to catch their faint signals. Telescopes are scouring dwarf galaxies for signs of wave-like dark matter's smoothing effect. And theorists are running simulations to see if fuzzy dark matter can reproduce the universe's large-scale structure. The story of dark matter's temperature is far from settled. But with ideas this bold, one thing's certain: the universe's invisible skeleton is full of surprises. And as we'll soon see, some of the most dramatic clues come from places where dark matter isn't just sitting quietly, it's crashing headlong into itself. Now, let's take a step back and look at a particle we actually know exists: neutrinos. Long before scientists were theorizing about WIMP or axions, neutrinos were the original candidates for hot dark matter. These ghostly particles are everywhere, streaming through the universe, and through you at nearly the speed of light. Born from the violent hearts of stars and supernova, they're so lightweight that gravity barely slows them down, earning them the hot label in the dark matter family tree. But here's the catch: neutrinos can't be the whole story. While they do behave like hot dark matter, zipping around too fast to clump into galaxies, there's simply not enough of them to account for all the missing mass in the universe. Think of it like trying to build a brick wall with a handful of confetti. Neutrinos are so light that even though trillions pass through your thumbnail every second, their combined mass is a tiny fraction of what's needed to explain the gravitational glue holding galaxies together. So why do they matter? Neutrinos give us a real-world blueprint for how hot dark matter behaves. Their frenetic speed means they smooth out small-scale structures, much like fuzzy dark matter's quantum waves. Computer simulations show that if dark matter were entirely made of neutrinos, the universe would look very different. Galaxies would be fewer and farther between, with large, washed-out halos. That doesn't match what we see, yet neutrinos' influence isn't zero. They leave a subtle fingerprint on the cosmic microwave background and slightly alter how galaxy clusters form, proving that even two light particles can shape the cosmos. This is where things get interesting. Neutrinos' shortcomings inspired scientists to explore hybrid models. What if dark matter isn't purely hot, cold, or warm, but a mix? Imagine a cosmic soup where most of the dark matter is cold and slow, like WIMP, but with a dash of something faster, like sterile neutrinos. These heavier cousins of ordinary neutrinos could split the difference, offering just enough heat to explain oddball observations without wrecking the large-scale structure of the universe. The hunt for sterile neutrinos is still on. Experiments like Mini-BU-NE and Fermi-LT are scouring data for hints of these elusive particles. If they exist, they'd bridge the gap between the neutrino's speed and the heft required for dark matter. It's a compelling middle ground, suggesting that the universe's invisible scaffolding might be more complex and more dynamic than we ever imagined. Neutrinos remind us that sometimes the key to unlocking a mystery lies in what we already know. They may not be the ultimate answer, but they light the path toward one. And as we'll see next, some of the most dramatic evidence for dark matter's temperature comes not from quiet corners of space, but from violent cosmic collisions. But to truly grasp the temperature of dark matter, we need to look beyond theories and simulations. We need real cosmic evidence, and nothing delivers that more dramatically than colliding galaxy clusters. Picture two massive cities of stars, gas, and dark matter smashing into each other at millions of miles per hour. These cosmic crashes aren't just spectacular, they're nature's ultimate physics labs revealing secrets about dark matter that we couldn't uncover any other way. Take the Bullet Cluster, one of the most famous cosmic collisions ever observed. This system, located about 3.7 billion light-years away, is the aftermath of two galaxy clusters plowing through each other like freight trains. Here's where it gets fascinating. When these clusters collide, their visible matter hot gas filled with stars slams together so violently that it heats up, glowing brightly in X-rays. But the dark matter, it doesn't play by the same rules. Observations show it cruises right through the collision, barely slowing down, leaving the visible matter lagging behind. Why does this matter? Because this separation is a smoking gun. If dark matter were hot like neutrinos zipping around at near light speed, it would spread out too much to stay concentrated in these collisions. If it were ultra cold, it would clump tightly around the visible matter. Instead, what we see is a Goldilocks scenario. Dark matter moves just fast enough to drift apart from the gas, but not so fast that it completely disperses. This suggests it's likely warm, with particles that have some speed but aren't racing chaotically. The Bullet Cluster also gives us clues about how dark matter interacts or doesn't with itself. The fact that it passes through the collision unscathed means it doesn't smash into other dark matter particles the way normal matter does. No friction, no heat exchange. This implies dark matter might have its own hidden rules of physics, a shadowy version of thermodynamics we're only beginning to probe, and this isn't a one-off. Other merging clusters like MAX J0025.4-1222 show similar dark matter behavior. Each collision is like a repeat experiment, confirming that dark matter's temperature and interactions are consistent across the universe. These observations even help rule out alternative theories like modified gravity, which can't explain why the gravitational lensing effects the bending of light always align with the dark matter's location, not the visible gas. So what's the takeaway? Collisions like the Bullet Cluster prove dark matter isn't just a placeholder in equations, it's a physical something with real properties, and its temperature plays a key role in how structures form. It's not blazing hot like a star, nor freezing cold like deep space. Instead, it occupies a mysterious middle ground, one that keeps galaxies from flying apart while shaping the universe on the largest scales. As we piece together these clues, another question arises. Could dark matter's temperature change over time, influenced by the expansion of the universe itself? That's a puzzle we'll explore next. Now, let's venture into one of the most mind-bending questions in modern cosmology. Could dark matter have its own hidden version of thermodynamics, a set of rules completely separate from the physics we know? The idea isn't as far-fetched as it sounds. After all, dark matter doesn't behave like ordinary matter. It doesn't collide, glow, or clump the way stars and gas do. So why would it follow the same thermal rules? Think of it like this. Imagine two parallel universes occupying the same space, one filled with the matter we see, governed by the laws of thermodynamics we've studied for centuries, and another shadowy realm where dark matter operates by its own mysterious playbook. Scientists call this hypothetical framework dark thermodynamics, and it could explain why dark matter's temperature doesn't align with anything in our visible universe. Here's where it gets even more intriguing. Some theories suggest dark matter particles might interact weakly with each other, not through the electromagnetic force, but through an entirely unknown force. These interactions could create a hidden thermal equilibrium, a balance of energy and motion entirely separate from the heat and pressure of ordinary matter. Picture a crowded room where everyone's chatting, but in two different languages. The visible matter is like people speaking loudly, bumping into each other, exchanging heat. Dark matter, meanwhile, is like whispers in a language we can't hear, communicating in ways that don't affect us but still shaping the room's hidden dynamics. This isn't just speculation. Observations of galaxy clusters and cosmic voids hint at this shadowy equilibrium. For example, in regions where dark matter dominates, its distribution is smoother than expected if it were completely cold, yet not so diffuse that it resembles hot dark matter. This just right spread suggests dark particles might be transferring energy among themselves, reaching a temperature balance invisible to us. One leading candidate for this behavior is a hypothetical particle called the dark photon. Unlike normal photons, which mediate electromagnetism, dark photons could carry a force exclusive to dark matter, allowing it to interact and potentially thermalize without ever touching ordinary matter. If true, dark matter wouldn't just be an inert backdrop to the universe. It'd have its own vibrant, invisible dance of energy exchange, but the real kicker. This hidden thermodynamics might leave fingerprints in the cosmic microwave background, the afterglow of the Big Bang. Tiny irregularities in this radiation could encode clues about how dark matter's temperature evolved over billions of years. Future telescopes, like the upcoming European Space Agency's Euclid mission, aim to hunt for these subtle patterns, potentially uncovering the first evidence of dark matter's private thermal rules. So what does this mean for our understanding of the universe? If dark thermodynamics is real, it implies a cosmos far more complex than we imagined, with parallel systems of energy and heat operating unseen. It's a reminder that dark matter isn't just missing mass, it's an entire hidden sector of physics waiting to be explored. And as we peel back these layers, we might find that the universe's greatest mysteries aren't in the stars above, but in the invisible threads weaving them together. Now let's zoom out from individual galaxies and take in the grand tapestry of the universe itself, the cosmic web. This vast network of filaments and voids, stretching across billions of light years, is more than just scaffolding for galaxies. It's a thermal fingerprint of dark matter's hidden heat. Picture the universe as a colossal spiderweb, with galaxies strung like dewdrops along its shimmering threads. The temperature of dark matter directly shapes this structure. If dark matter were colder, its particles would move sluggishly, clumping tightly around galaxies and deepening the gravitational wells between them. The result, a web with exaggerated knots and gaps like a knotted rope pulled taut. But if it's warmer, those particles zip around faster, smoothing out the densest clumps and leaving a more even distribution. Think of a gentle ripple across a pond instead of jagged waves. Here's where the real magic happens. Supercomputer simulations of cosmic evolution reveal a striking mismatch when we assume dark matter is purely cold. The models predict an overabundance of dwarf galaxies and overly dense filament structures we simply don't observe in the real universe, but tweak the simulation to include slightly warmer dark matter. Suddenly, the virtual cosmos starts resembling our own with fewer dwarfs and a silkier web. It's as if the universe is whispering, "Your models are close, but you're missing the heat." Observations back this up. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing a cosmic web that's neither too clumpy nor too smooth. The Goldilocks-like balance suggests dark matter particles aren't racing at near-light speeds like neutrinos, which would erase small-scale structures entirely or barely moving like heavy, cold candidates. Instead, they might occupy a middle ground, particles with just enough warmth to resist extreme clumping, but enough gravity to sculpt the web's delicate threads. One fascinating clue lies in the voids, the empty bubbles between filaments. These regions aren't perfectly barren. They contain faint traces of galaxies flung there like scattered seeds. If dark matter were colder, these voids would be emptier still, as gravity would have sucked every last speck of matter into the denser filaments. But the sparse galaxies we do see suggest a slight repulsion, a gentle push from warmer dark matter's kinetic energy preventing total collapse. The implications are profound. If dark matter's temperature truly molds the cosmic web, then studying the universe's large-scale structure becomes a way to take dark matter's temperature without ever touching it. Telescopes like the upcoming Euclid and Vera C. Rubin Observatory will scrutinize distortions in the web's pattern, hunting for subtle warping that betrays dark matter's thermal quirks. It's like reading the universe's thermal map to uncover the secrets of its invisible architect. So what's the takeaway? The cosmic web isn't just a static backdrop. It's a dynamic thermal canvas painted by dark matter's hidden heat. And as we decode its patterns, we're not just mapping the universe, we're taking the temperature of the unknown. Now, let's consider another cosmic puzzle piece, dark energy. While dark matter's heat shapes the universe's structure, dark energy is the mysterious force causing the cosmos to expand faster and faster. But here's the twist. These two invisible giants might be in a silent dance, with dark energy's relentless push indirectly influencing dark matter's temperature. Think of it like this: as dark energy stretches space itself, it's not just galaxies that move apart. Dark matter particles are also carried along like leaves on an accelerating river. But unlike leaves, these particles interact gravitationally, and their motion generates heat. Over billions of years, could dark energy's expansion be subtly warming dark matter? Some theories suggest yes. Take speculative models where dark matter's temperature isn't static but evolves with the universe's expansion. In the early cosmos, dark matter was likely denser and colder, clumping easily to form the first galaxies. But as dark energy took over, its push might have stirred dark matter particles, giving them extra kinetic energy, effectively turning up the heat. This could explain why modern galaxies sit in fluffier halos than expected. Their dark matter has warmed up over time. Then there's the counterintuitive idea of dark thermodynamics. If dark matter particles interact weakly with each other, say, through an unknown force, they might establish their own thermal equilibrium, separate from ordinary matter. Dark energy's expansion could disrupt this balance, injecting energy into the dark sector and raising its temperature. Observational clues are scarce but tantalizing. For instance, the rate of galaxy cluster formation has slowed more than expected in recent cosmic epochs. Cold dark matter models struggle to explain this, but if dark matter warmed as dark energy dominated, Its increased motion would make it harder for clusters to collapse, neatly matching observations. Of course, this is frontier science full of what-ifs. Alternative models propose that dark energy and dark matter might even exchange energy, like two cosmic engines linked by invisible gears. Others suggest dark energy's influence is negligible, leaving dark matter's temperature unchanged. The truth, we're still piecing it together. What's clear is this: dark energy isn't just stretching the universe, it might be quietly cooking dark matter, reshaping the cosmic web in ways we're only beginning to grasp. Upcoming telescopes like Euclid could spot telltale signs of this heating by measuring how galaxy clustering changes across cosmic time. Until then, the interplay between these two shadowy forces remains one of cosmology's most thrilling open questions. So while dark matter's heat sculpts the universe's skeleton, dark energy might be the hand turning up the thermostat. And if they're truly intertwined, unraveling their relationship could rewrite our understanding of cosmic evolution. Now, let's shift our focus to the cutting-edge experiments hunting for dark matter particles. While theories and simulations give us clues, nothing beats real-world detection, and that's where projects like Xenon and LUX come in. These aren't just high-tech gadgets, they're cosmic detectives designed to catch the faintest whispers of dark matter interacting with ordinary matter. Here's the catch: dark matter's temperature plays a huge role in whether we can spot it. Think of it like trying to catch fish in a river. Warmer dark matter particles move faster, like energetic trout darting through the water. They're harder to pin down because their speed makes interactions fleeting. On the other hand, colder dark matter particles are slower, like sluggish catfish, easier to detect but with a catch. Their lower energy means they leave subtler traces, requiring ultra-sensitive equipment to spot them. Experiments like Xenon and LUX use massive tanks of liquid xenon, buried deep underground to shield from cosmic noise. When a dark matter particle bumps into a xenon atom, it should produce a tiny flash of light and a jolt of electricity. But the warmer the dark matter, the faster those particles zip through the detector, reducing the chance of a collision. That's why some models suggest focusing on colder dark matter. It lingers longer, increasing the odds of a detectable hit, but temperature isn't just about speed. It also affects the energy signature. Warmer particles pack more kinetic energy, so if they do collide, they might create a louder signal like a drumbeat in a quiet room. Colder particles, meanwhile, might leave faint, low-energy ripples akin to a whisper. That's why detectors must be tuned to a wide range of energies, ready to catch anything from a shout to a murmur. Indirect detection adds another layer. Instead of waiting for dark matter to come to us, telescopes like Fermi and AMS-02 scan the skies for byproducts of dark matter collisions, gamma rays, antimatter, or neutrinos. If dark matter is warmer, those particles might be more spread out, like embers from a distant fire. Colder dark matter could clump more densely, creating brighter, more concentrated signals. Yet, despite decades of searching, no experiment has definitively bagged dark matter. Is it because we're looking for the wrong temperature, or are our detectors just not sensitive enough? The answer might lie in next-generation projects like Darwin, which aims to cast an even wider net, or quantum sensors that could pick up the faintest tremors of a dark matter interaction. One thing's certain: the hunt is far from over. Whether dark matter is hot, cold, or somewhere in between, each experiment brings us closer to unmasking this cosmic ghost. And when we finally catch it, the revelation won't just solve a puzzle, it could rewrite the rules of particle physics. Now, let's dive into some of the biggest cosmic mysteries that have left scientists scratching their heads, observations that cold dark matter alone can't quite explain. These astrophysical anomalies aren't just minor hiccups in our understanding. They're glaring puzzles that challenge the very foundation of how we think dark matter behaves. Take the case of missing satellite galaxies. According to simulations, if dark matter is purely cold, our Milky Way should be surrounded by hundreds of tiny satellite galaxies, far more than we've actually spotted. Astronomers call this the missing satellites problem. It's as if we're expecting a bustling crowd but only seeing a handful of people. Where are the rest? Some researchers believe the answer lies in dark matter's temperature. If dark matter is slightly warmer, not too hot, not too cold, it could suppress the formation of these small galaxies, smoothing out the cosmos just enough to match what we observe. Then there's the puzzling stability of galaxy disks. Spiral galaxies, like our own Milky Way, rotate so fast that their outer stars should be flung into space, yet they hold together perfectly. Cold dark matter models predict these disks should be far more clumpy and warped than they actually are. But if dark matter has a bit of warmth, its particles could move just fast enough to distribute more evenly, providing the gentle gravitational scaffolding needed to keep these delicate structures intact. Another head-scratcher is the cusp core problem. Cold dark matter simulations suggest that galaxy halos should have dense, steeply rising centers like a mountain peak. But observations reveal softer, flatter cores, more like rolling hills. Warmer dark matter could be the key. Its particles, moving with a bit more energy, might push outward slightly, smoothing those sharp cusps into gentler profiles that align with real galaxies. And let's not forget ultra-diffuse galaxies. These faint, wispy collections of stars seem to defy expectations. They're too large and spread out to exist in a universe dominated solely by cold dark matter. Yet, if dark matter has a touch of warmth, it could explain their ghostly, stretched-out forms, as particles with a bit more energy resist collapsing into tight knots. These anomalies aren't just academic curiosities. They're forcing cosmologists to rethink dark matter's fundamental nature. Could it be that dark matter isn't strictly cold, but somewhere in the warm, sweet spot? The debate is far from settled, but each observation nudges us closer to an answer. Some scientists double down on cold dark matter, tweaking models with complex astrophysics. Others explore hybrid theories, blending warm and cold components, and a few even consider entirely new particle candidates that behave unlike anything we've imagined. What's clear is this: every unexplained galaxy, every oddball observation, is a clue in the greatest detective story of all time. The universe is leaving us breadcrumbs, and the temperature of dark matter might just be the thread that ties them all together. Now, let's venture into one of the most fascinating what-ifs in modern astrophysics, the idea of dark stars. Imagine a star not powered by nuclear fusion like our Sun, but instead glowing from the annihilation of dark matter particles. It sounds like science fiction, but some theories suggest these exotic objects could have existed in the early universe, and their existence would tell us a lot about dark matter's temperature and behavior. Dark stars, if they're real, would be colossal beasts. Picture a star hundreds or even thousands of times more massive than our Sun, radiating not from the fiery reactions of hydrogen and helium, but from the slow, steady decay of dark matter particles colliding and annihilating within their cores. These wouldn't be the twinkling points of light we see in the night sky. Instead, they'd emit a diffuse, eerie glow, powered entirely by the invisible stuff that makes up most of the universe. But how would such a star form? Here's where dark matter's temperature comes into play. If dark matter is warm enough to move at moderate speeds but still cold enough to clump together under gravity, pockets of it could have gathered in the early universe, seeding the birth of these bizarre objects. As ordinary matter, hydrogen and helium fell into these dark matter halos, the heat from annihilation would prevent it from collapsing into a dense, fusion-powered core. Instead, the dark matter would keep the gas puffed up, creating a star that's massive yet strangely cool on the surface, like a dim, smoldering ember in the cosmos. The energy release mechanism is another critical piece of the puzzle. Dark matter annihilation produces energy differently than fusion. In a regular star, fusion happens in a raging, turbulent core. But in a dark star, annihilation would be spread throughout its vast interior, releasing energy more uniformly. The exact amount of heat generated would depend on the type of dark matter particles involved. If they're heavier and slower closer to cold dark matter, they'd annihilate less frequently, producing a gentle but sustained energy output. If they're lighter and faster, leaning toward warm dark matter, the annihilation rate could be higher, potentially making these stars brighter or shorter-lived. Interestingly, dark stars might not even look like stars in the traditional sense. Without the intense surface temperatures of fusion-powered suns, they could appear as giant, foggy orbs, their light redshifted and stretched by time. Some models even suggest they could exist today, lurking undetected in the distant universe, their faint glow lost in the sea of background radiation. The hunt for these cosmic oddballs isn't just about satisfying curiosity. If astronomers could find evidence of dark stars, it would be a smoking gun for specific dark matter particle properties, especially their mass and temperature. Telescopes like the James Webb Space Telescope are scanning the early universe for objects that match these predictions. Spotting one would revolutionize our understanding of dark matter's role in cosmic evolution. Of course, dark stars remain speculative. No confirmed detections exist yet, and some theories suggest they might be too rare or too short-lived to find. But the mere possibility opens a thrilling window into physics beyond our current models. Whether or not they're out there, the concept pushes us to ask deeper questions. What if dark matter isn't just an invisible scaffold but an active participant in the universe's energy budget? Could it have shaped the first stars in ways we're only beginning to imagine? The search continues, and with every new observation, we edge closer to answers or perhaps to even bigger mysteries. But here's something that might surprise you. The tools we have today are just the beginning. The next generation of telescopes and space probes could be the key to finally cracking the mystery of dark matter's temperature. And the race to uncover this elusive truth, it's already heating up. Take the James Webb Space Telescope, for instance. This isn't just another space observatory. It's a game changer. With its unprecedented sensitivity to infrared light, Webb can peer farther back in time than any telescope before it, capturing the faint glow of the universe's first galaxies. Why does that matter for dark matter? Because those early galaxies formed in the densest regions of dark matter halos. By studying their shapes, sizes, and distribution, Webb could reveal subtle clues about how dark matter behaved in the early universe, whether it was clumping tightly like cold dark matter or smoothing out like warmer varieties. Then there's Euclid, the European Space Agency's dark matter detective. Unlike Webb, which focuses on deep space imaging, Euclid is designed to map the cosmos in 3 dimensions, charting the positions of billions of galaxies across 10 billion light-years. How? By measuring gravitational lensing, the way dark matter bends the light from distant galaxies as it passes by. The finer the distortions Euclid can detect, the more precisely we can map dark matter's distribution. And here's the kicker: the way dark matter clumps or spreads out is directly tied to its temperature. Warmer particles move faster, creating fluffier halos, while colder ones settle into dense knots. Euclid's data could finally tell us which one dominates, but the hunt doesn't stop there. The Nancy Grace Roman Space Telescope, set to launch later this decade, will take wide-field surveys of the sky, hunting for the faint imprints of dark matter on the cosmic web, the vast filamentary structure of the universe. By comparing these observations to supercomputer simulations, scientists can test whether dark matter's temperature aligns with predictions. Even ground-based telescopes like the Vera-C. Rubin Observatory are joining the effort, scanning the sky nightly for gravitational lensing effects that might betray dark matter's thermal fingerprints. The stakes couldn't be higher. Pinpointing dark matter's temperature isn't just academic, it's a missing piece in our understanding of how galaxies form, how the cosmic web evolved, and even how the universe might end. If dark matter is warmer than we thought, it could explain why some small galaxies are missing or why certain cosmic structures appear smoother than simulations predict. On the flip side, if it's colder, that might mean our models need a major overhaul. What's truly exciting is the collaborative nature of this search. No single telescope can solve the puzzle alone, but together they form a cosmic detective squad, each bringing unique skills to the table. Webb peers into the ancient past, Euclid maps the universe's skeleton, Roman scans for hidden patterns, and Rubin monitors the sky in real time. It's a coordinated assault on one of science's greatest mysteries, and the clock is ticking. Every new observation narrows the possibilities, bringing us closer to answers, or perhaps to even deeper questions. Because in the end, that's how science moves forward. Not with a single eureka moment, but with painstaking steps, each one building on the last. The tools are ready. The data is coming, and somewhere, hidden in the whispers of the cosmos, dark matter's temperature is waiting to be discovered. Now let's step back and consider what all this means for our place in the cosmos. The temperature of dark matter isn't just a technical detail. It's a profound clue about the fabric of reality itself. If dark matter turns out to be warmer than we've assumed, it could rewrite not just our astrophysics textbooks, but our entire understanding of existence. Think about it this way: for decades we've pictured dark matter as a passive cosmic scaffold, silently shaping galaxies without interacting with them. But what if it's not so simple? Warmer dark matter suggests particles moving faster, potentially interacting more not with ordinary matter, but with itself. This opens the door to a hidden dark sector, a shadow universe with its own rules, forces, and maybe even structures we can't yet imagine. It's like discovering that the silent background character in your favorite show has a rich, complex life off camera. And here's where it gets really mind-bending. Some theories propose that dark matter's warmth could be a sign of extra dimensions, tiny, curled up layers of space that influence how particles move and interact. In this scenario, what we perceive as dark matter's temperature might actually be the fingerprint of higher dimensional physics playing out right under our noses. It's not just about invisible matter anymore. We're potentially glimpsing the architecture of reality beyond our three-dimensional experience. This cosmic detective story ties directly into humanity's oldest questions. Every culture has myths about unseen worlds, from spirits to parallel realms. Today's science might be uncovering something equally astonishing, a hidden sector of the universe that's been here all along, invisible yet indispensable. The realization that we're surrounded by, even made possible by, something we can't see or touch is humbling. It reminds us that the universe has layers of mystery we're only beginning to peel back. Consider, too, what this means for life's chances across the cosmos. Dark matter's temperature shaped where galaxies could form, how quickly stars ignited, and ultimately where the ingredients for life could emerge. If it had been colder, the universe might be clumpier, with life isolated in dense islands. Warmer, and structure might have been too diffuse for galaxies to form at all. We're here because dark matter, whatever its temperature, struck a cosmic Goldilocks balance. That's not just science. It's a profound connection between the quantum rules of invisible particles and the emergence of conscious beings able to ponder them. As we stand on the verge of potentially groundbreaking discoveries, remember this: solving dark matter's temperature isn't about checking a box on a scientific to-do list. It's about uncovering whether the universe is simpler or vastly more complex than we've dared to dream. Every time we think we're close to understanding reality, the cosmos reminds us we've only scratched the surface. And that's exhilarating, because in the end, we're not just searching for dark matter's secrets, we're searching for our own story written in the stars. Now let's set the record straight on some persistent myths about dark matter's temperature, because misunderstandings here can cloud the bigger picture. One of the most common assumptions is that dark matter must be freezing cold, floating through space like cosmic ice, but that's not quite right. While it's true dark matter doesn't behave like ordinary matter, its temperature isn't about freezing or burning in the way we're used to. Think of it this way: when we say dark matter is hot, we're not talking about heat you could measure with a thermometer. Instead, we're describing how fast its particles move. Fast-moving particles mean hotter, dark matter, even if they're not radiating warmth like a star. Another myth worth tackling is the idea that dark matter might just be ordinary matter we haven't spotted yet, like rogue planets or cold gas clouds. But if that were true, we'd see their gravitational effects in very specific ways, something our telescopes and simulations have ruled out. Dark matter's behavior, especially its temperature clues, points to something far more exotic. It doesn't clump like gas or planets. It forms vast, smooth halos around galaxies, a telltale sign of particles that move too quickly to collapse into dense structures. That's why scientists are confident it's not just hidden ordinary matter. Here's where things get even more interesting. Some people hear hot dark matter and picture it glowing or emitting energy like a furnace. But dark matter's heat is entirely different. It's a shadowy kind of energy, invisible to our eyes and instruments. The warmth we're discussing isn't about fire or light, it's about motion on a subatomic scale. Imagine billions of tiny particles zipping through space, their speed shaping the universe's structure without ever bumping into each other. That's the kind of heat we're dealing with. Then there's the misconception that dark matter's temperature is fixed, unchanging since the Big Bang. Actually, some theories suggest it could have cooled or heated up over time, depending on how it interacts with itself or other invisible forces. This isn't like a cup of coffee losing heat. It's more like a cosmic dance where the steps evolve over billions of years. If dark matter particles can exchange energy in ways we don't yet understand, their temperature could hold clues about the universe's hidden layers. Let's not forget the most poetic myth of all, that dark matter is just empty space or a placeholder for our ignorance, but the evidence tells a different story. From the way galaxies spin to the patterns in the cosmic microwave background, dark matter's gravitational fingerprint is everywhere. Its temperature, whether warm, cold, or somewhere in between, isn't a gap in our knowledge. It's a puzzle we're actively solving, piece by piece, so the next time someone claims dark matter is freezing cold or just unseen gas, you'll know the truth. Its heat isn't about traditional fire or ice. It's a window into the universe's hidden rules, written in the language of particle motion and quantum uncertainty. And that's what makes this mystery so thrilling. It's not just about what dark matter is, but what it reveals about everything else. Now, let's bring it all together. Dark matter isn't the icy, inert ghost we once imagined. Clues from galaxy rotations, cosmic microwave background anomalies, and even the puzzling behavior of dwarf galaxies all point to something far more dynamic. Its particles might not blaze like stars, but their speed, their hidden energy, shapes the universe in ways we're only beginning to grasp. The old idea of dark matter as a frozen, passive scaffold just doesn't fit the data anymore. Instead, think of it as a cosmic sculptor, its warmth subtly molding the vast structures we see across the cosmos. And here's the kicker. If dark matter is warmer than we thought, what does that mean for everything else? Could there be entire layers of physics, unseen forces or particles, dancing just beyond our current understanding? The universe loves surprises, and dark matter's temperature might be the first clue in a much larger mystery. So the next time you look up at the night sky, remember, what we see is only a fraction of the story. The real action is happening in the shadows, where dark matter's invisible heat weaves the fabric of reality itself. If that doesn't blow your mind, I don't know what will. If you've enjoyed this cosmic deep dive, don't forget to hit that subscribe button and ring the bell for more mind-bending journeys into the unknown. The universe is full of secrets waiting to be uncovered. Let's explore them together. Until next time, keep looking up and wondering what else is out there just beyond our sight.